Hey guys, welcome back. Today we're going to be talking all about chemical formulas. So to start off, you may be asking what a chemical formula is. And a chemical formula is a way for us to have a pretty much language in chemistry where we can understand, one, what is in a compound, and two, how much of something is in a compound. So for example, H2O, we have two hydrogens and one oxygen. That would be an example of a compound. Now within chemical compounds, we have two types. We have molecular and we have empirical. So a molecular compound is going to be pretty much your exact number of however much of a certain atom is in the compound. So let's go with exact number as our definition. And our empirical formula is going to be the simplest ratio of that exact number. Molecular formulas are typically used in everyday chemistry. Like, if you're having something on a test, it's going to be molecular formula. If you're doing a quiz question, it's going to be molecular formula. If you're looking at a bottle of a compound, it's going to be molecular formula. Empirical formula usually comes around whenever we're trying to find an unknown. So there's certain types of instrumentation methods where you can figure out what compounds are actually in an unknown, just not how much of them. So using empirical formulas, we find the simplest, just what the compounds are, and then we can do certain experiments to figure out how much of each thing, giving us our molecular formula. So to further explain this, I want to kind of give you an example. So hydrogen peroxide is the formula H2O2. So two hydrogens and two oxygens. That's your molecular formula. Your empirical formula, because it's the simplest ratio, is actually just HO. And if we're thinking about HO, that could be plenty of things. That could be hydroxide, that could be water, it could be hydrogen peroxide. There's endless possibilities of what that HO could be, but if we do the certain experiments, we can figure out that there's two hydrogens, two oxygens, giving us our hydrogen peroxide. Moving on, we're going to talk about some different types of compounds. So our first main type of compound is what is known as an ionic compound, with the base word as ion, an atom with a charge. So when talking about ionic compounds, we have two components of them. A cation, which always comes first, and an anion, which always comes second. We've talked about it in previous videos, but I want to just review this. A cation is an ion with a positive charge, and an anion is an ion with a negative charge. You could think of this as a T for plus, or a cat makes you happy, an onion makes you sad, whatever you want to do to remember. But a cation is a positive charge that always comes first, and an anion is a negative charge that will always come second. So when talking about certain compounds, such as sodium chloride, for example, which is just table salt, it actually looks like this, NaCl. Sodium being Na, Cl being chloride. Whenever you're talking about an anion and you're trying to name a certain compound, you're going to change the ending to whatever to "ide." So chlorine, in this case, became chloride. Chlorine to chloride, bromine to bromide, sulfur to sulfide, phosphorus to phosphide, oxygen to oxide. Every time your anion in an ionic compound is going to end with IDE. Your cation will always stay the same, so like we were saying, sodium chloride, not sodium chlorine, sodium chloride. Moving on to charge. So if we're looking at the periodic table, sodium is going to be in what's known as group 1A, as we talked about in previous videos. And all atoms in group A, or ions, I guess I should say, have a +1 charge. On the other hand, chlorine, a member of group 7A, the halogens, is an ion with a -1 charge. Usually, if we're talking about just 1 and 1, you can put just plus or minus. It's up to you, though. It's just a bit easier. Now that we have identified sodium with its +1 charge and chlorine or chloride with its -1 charge, what we do is we actually cross our charges to opposite sides. So the +1 of chlorine goes here, we put a little 1 here. And the -1 of chlorine goes to sodium. So our ending answer is going to be Na1Cl1, or to simplify it, NaCl. Let's do another quick example. Let's say we're talking about something very similar, calcium chloride. Calcium is a member of group 2A, so it's going to have a 2+ charge. And chlorine, as we stated before, is a member of group 7A, the halogen, so it is still going to have that -1 charge. If we take our charges and switch them across, so our 2+ to chlorine, our -1 to calcium, we throw our 2 here, our 1 there, our final answer is going to be Ca1Cl2, or just CaCl2, calcium chloride. So this is pretty much saying that the 2+ charge from calcium is going to take 2 chlorines to make it even, right? We're trying to make this overall thing even. We're trying to make all the electrons happy. So if we have a calcium with a 2+ charge, so we have 2+ over here, and then we have a -1 charge from chlorine, and we have 2 of them. That's going to be +2 and then -2, which gives us our overall 0 charge that all things strive to be. Everything wants to be as stable as possible. Another cool little fact about ionic compounds, typically, and not always, but typically, they're actually going to be their empirical formula. It's kind of different than when we talk about other types of compounds, but ionic compounds usually are the empirical formula, as we talked about earlier. And lastly, I want to talk about ionic compounds with these things known as polyatomic ions. So polyatomic ions are ions with 2 or more atoms. So there's countless different ones, but they usually have a set charge, or they pretty much always have a set charge. So some examples could be nitrate, NO3 minus. So this entire thing, NO3, has a -1 charge. Not just the nitrogen, not just the oxygen, the entire NO3 has that negative charge. PO4, 3 minus, that's phosphate. The entire PO4 has a 3 negative charge. What else? We could do SO4, 2 minus. Sulfate, the entire SO4 has a 2 minus charge. So whenever we're talking about ionic compounds with these sort of polyatomic ions, it's important to remember that the entire charge is going to cross over. So let's go back to our calcium example. So let's say we're talking about calcium and phosphate, so PO4, 3 minus. As we talked about before, calcium is a member of group 2A, the alkaline earth metals, so it's going to have that 2+ charge. And remember, the PO4, 3 negative is for the entire PO4, not just the oxygen, not just the phosphate. The entire PO4 gets a 3 negative charge. So this 3 negative is going to go over to calcium, and this 2 positive is going to come all the way over to the entire PO4. Now there's one common mistake that a lot of you are going to try to make here. You're going to put PO4, 2. And if you're thinking like in a mathematical sort of way, this just looks like 4 times 2 or 42 or anything else, but it's not the answer that we're looking for. So what we actually do is we put parentheses around PO4, stating that the entire PO4 gets the 2, and then our calcium over here gets our 3. So your formula for calcium phosphate is going to be Ca3PO42. And I want you to realize I didn't say phosphide. I didn't, the phosphate name sticks. Whenever we're talking about polyatomic ions, it's going to stick. When I'm talking about calcium sulfate, it's going to be sulfate, not calcium sulfide. When I'm talking about calcium nitrate, NO3-, it's still going to be calcium nitrate, not calcium nitride. But yeah, let's move on to another example. Let's do calcium sulfate right here. So when talking about calcium sulfate, there's a bit of a unique difference here that adds a bit of an extra step, but let's go on and do it anyways. So calcium gets that 2+ charge because it's a group 2A element, and sulfate is SO4 2-. Now, when we cross over these charges, giving us that +2 with our sulfate and our -2 with our calcium, we get Ca2SO4 2, and don't forget your parentheses. Now, as we talked about, a lot of our ionic compounds are empirical formulas, so it's important for us to actually cancel these out because we want that simplest ratio. So what we actually would do is we would do this. Cross out our 2's, making them both 1's. This formula is actually going to be CaSO4 without any parentheses, calcium sulfate. It's important whenever we're doing nomenclature to do a lot of practice problems. I know it seems either easy or tedious, whatever you may feel depending on your comfortability with the subject. But it's important that we do practice. There's always going to be those problems. There's always going to be those different types of things that make it a little bit harder. But I'm going to link the link down below to do some practice problems. I'll have a bunch attached. Hopefully those can help you review for your quizzes, for your exams, whatever you may need. And before we head out, I want to go over one more topic, transition metals. So if you watch the periodic table video I posted a few videos back, you'll see that we talked about the transition metals. And I stated that the transition metals had some different properties, didn't really get into it, but now we're going to talk about those. So the reason that they're called transition metals is because the charges aren't set. There isn't like a set charge, like where it's group 1A, it's a +1, where it's group 2A, it's a 2+, or if it's group 7A, it's a -1, or so on and so forth. The transition metals actually transition between charges. So iron being a transition metal is a very, very common example. Iron has the chemical symbol as Fe for the atom. Now, whenever we're talking about an iron ion, there's two types of ions. Both of them are cations, but they have a different charge. One is 2+, one is 3+. So the 2+ iron charge is actually known as ferrous ion, and the Fe3+ is known as the ferric ion. So they are a bit similar, but they are different. They do have a different charge, and they do call for different types of naming. Whenever we're talking about transition metals, it's important to remember that we're always going to use a Roman number every time we're talking about a transition metal. So the number that you use correlates directly to whatever the charge on your metal is. So if we're talking about an Fe2+, we're going to use a 2+ with parentheses around it. If we're talking about a 3+, we're going to use a 3 with parentheses around it. And besides that, you name it the exact same way you would name any other ionic compound. So let's say we're talking about iron 2 chloride, right here. Iron 2 chloride. So what we would do is we would take our iron 2, our ferrous ion, giving it that 2+ charge, and we would take our chloride ion with that -1 charge, because it's a group 7A, halogen, and we're going to cross over our 2+ and our -1, giving us FeCl2. FeCl2 means iron 2 chloride. Now if we're working backwards, And like I can give you this name up here. Let's say I don't give you that. You're going to be asked sometimes to name what this is. And if you look at your periodic table, you're going to see iron in the transition metals, and you're instantly going to think Roman numeral. So what you do is you pretty much work backwards. So if I have FeCl2, I'm trying to figure out what that is. All I'm going to do is I'm going to reverse those charges, giving it me right back to Fe2 plus Cl minus. I know that 2 plus means iron 2 chloride. Let's see one more example. Let's talk about iron 3 nitride. Iron 3 nitride. So, since we have iron 3, we know that means it's going to be ferric, Fe 3 plus. And nitride, because it is a group 5A, is going to have a 3 negative charge. And we'll do the same exact thing as we've done before, moving our charges to opposite sides. Fe3 and 3, but since we're looking for the empirical formula, we're going to cancel, giving us FeN, iron 3 nitride. Now you may be saying, as we talked about before, moving backwards. Let's say all I give you is FeN. You're thinking, where's the 3? How are you going to know it's a 3? So here's what you would do in this situation. It's going to take a bit more thinking. So if we're looking at this and we separate our two things, we know that we're going to have an Fe, and we know that we're going to have an N. Both of these things are 1, as of now, because we're an empirical formula. We definitely know nitrogen has a set ionic charge, which is 3 minus. If we want to figure out what made these things both get to 1, we need to just say, okay, what canceled that out? So we know that our iron is going to have a 3 plus charge, giving us, again, iron 3 nitride.